Should be dependent upon the chipset, not the
Yeah.
OS.
So it's a CPU hardware level problem.
So now we're gonna look at the instruction set architectures, right?
That is what it's called. Yeah, that's it.
We see some stuff that different software will use a little ND, and even the NDs they'll probably use.
Well, yeah, I mean, your
Yeah,
software
like-
has to be compatible to the whatever NDMS the architecture has.
So instruction set architecture, it's gonna be efficient or not based on the memory space, instruction complexity, instruction length, and total number of instructions. Okay. So when we design, we consider the instruction length, whether it's short or long or variable. We also look at how many operands do we need, right? Like in Mary architecture, we have only one operand, right? But yeah, in Microsoft Assembly, we have two, right? Right. So it depends on if it they call assembly, some assembly.
So x86 somewhere.
Yeah.
I can bring up an
So like this book talk about another type of assembly. This is a good book too.
Yeah, this one like.
Yes.
Oh, okay.
X86 instructions. This one, let me show you. There's some assembly that's come with this book that they use to talk about architecture. They didn't use Mary assembly. They used the
For the
x86.
love of God, use x86. I think it's a different one.
Different.
So this is pretty much the same. Just start with, yeah, that's the assembler, right? MIPS, right? Assembly language for MIPS means MIPS. See that this is the operand, right? And these are three operands, right? I mean, opcode and three. Add, like in Mary, you have just one operand, right?
Yeah.
This one add 2, 4, 2, right? So it's pretty much add register. Now you have to look at, like, add can be just two operand to add A to B, right? Like that. Not like Mary. This is just another type of. This is MIPS. Right, but now you pretty much just need to see what are those, right? When you read, same as Mary, right? Add this to AC, right? Add X to AC. Now we have to know. Yeah, this is just showing the hardware performance, how to calculate. We talk about those, right? But I just want to skip to the more into here. This is also another one, right? Add C 1, 2, 3 operand. So right, register T0 contains G plus H. It's just like you add S1 to S2 and store into T0. So this is three operands, right? So three registers, right? Right, you add S3 to S4 and contains in T1, right? So this is the MIPS, right? MIPS. You can subtract T0 from T1 and then store into S0 result. So that's different example. Make sense? Another instruction set architecture, right? So that's why this is number of operands, number of addressable registers. So in Mary, I have 12 bits, right, addressable. If I want to increase more operands, I could. Then I have 11 bits addressable left. Right, so those are trade-offs that we have to look at, right? And memory organization, byte over addressable, right? Addressing modes, direct, indirect, or indexed. Right, so we have load I, that's like indirect, right? Add I, right? Add is like direct, right? Load direct. And then you can do index, just go to that location directly, right? Also, byte ordering or endianness. Byte ordering, that means lower. So, like this one, right? We have 2 byte, right? Integers. Integer may be stored so that the least significant byte is followed by the most significant byte. Okay, so that's called little endian. Big endian is the most significant byte first and then the least, right? So for example, we have this hexadecimal number, right? 1 to 8. So in big endian, it's just store 1, 2, 3, 4, 5, 6, 7, 8. But little endian is going to go to the least significant first, which is 7, 8, 5, 6, 3, 4, and 1, 2. Right? Right, this is the address location. It's just go to 00 store 78, 01, right? And 02, I mean 10, right? And 11. So that's the little endian, right? And this is giving example of a computer that uses 32-bit integers. Right, and this is the value that's going to store. So if it's big endian, it's just go at address location, right? Just A, B, C, D, E, and so on, right? But if it is a little endian, it's going to go with 34 first and 1, 2, and CD, right? So said big endian is more natural. Yes, when you read, it's easy to read, right? The sign of the number can be determined by looking at the byte at address offset 0. String and integers are stored in the same order, right? How about little endian? Make it easier to place value on non-word boundaries. Okay. So the side of the word, right? I think when we said non-word boundaries. So the size, let's say if we have, what's the word size? 32, 64, 16, right? Okay, 16. Right, 4 hex. So if you want to place this, let's say if we have one, if I want to start A, B, C, D, right? So what happens if we only have 200 empty, but 201 is not empty? So it's going to be AB and then skip to the next available and then do CD.
And the big endian. Or no.
But for little endian, if I say, okay, CD here, then just find the next one and do AB, right?
This is 32-bit integers, so it should be clear.
So word boundary means, so this is for each word, right? And there's a boundary between the word, right? Mm-hmm. So if you want to say the word has to be consequent, right? I mean, next to each other, then in that case, you probably has to have a lot of gaps, right? Or we call fragments, right?
Yeah.
But in big endian, since it's not in that order, then you can just put the back one first. That's what I think. That's what it means. Then
I'm not.
you can just put in the next one. Or if you look at your textbook, it may explain more. Can you look in details? Okay, benefits. Okay, this one also talk about that. There are arguments either way, but one point is that in a little endian system, the address of a given value in memory take as 32, 16, or 8-bit width is the same. In other words, you have in memory a 2-byte value, right? Taking that 16, a 16-bit value, short,
A byte. Is this?
or as an 8-bit value, right? C sharp changes only the fetch instruction you use, not the address you fetch from. A big endian system with a bulk layout as this is big, right? 0 has to go first, right? You would need to increment the pointer and then perform the narrow fetch operation on the new value. On little endian system, cast are and no op. So let's look at the question a little bit maybe. Intel processors use the little endian format for storage. Well, I always wonder why someone would want to store the bytes in reverse order. Does this format have an advantage, right, over the big endian?
Okay, so if in big endian you're trying to retrieve something, it's like 0.0000005642. You have to go through all the zeros.
Right.
But on little endian, you start with the numbers, and as soon as you get to the zeros, you can just skip that kind of portion. That's what I'm understanding. That with little endian, you start with the value first.
One points that in little endian system, the address of a given value in memory taken as 32, 16, 8. Yes, all the same, right? Why is it the same? Because
Loads the home.
yeah, like 32-bit, 16-bit, or 8-bit, I always go to the first index and get it, right? But if you want to load 32 bits in big endian, is slower because you have to increment to that index. That makes sense? Okay, you got it. So that's probably that. This is what it means too. Right, so if I want to store 8-bit, right, I can just store into the first index. I don't have like on top of the word, right? I can just store it on the first index and then 00 on the second right index, right? I don't have to increment to start the bottom and then go to the first. It's just, yeah, does that make sense, right? It's just you don't have to reverse the process for the computer. All right, so conversion from a 16-bit integer address to a 32-bit integer address does not require any arithmetics.
Yeah.
Right.
You can just
Mm-hmm.
extend it.
You just extend it right away. But for the big endian,
You have to rewrite
the whole thing, the index gonna change, right? From 2 bytes to 8 bytes, you have to shift them. All right, so the next consideration for architecture design concern about how the CPU will store data, right? Are you going to use stack architecture? Stack is push, 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 push in, right? Or you're gonna use the accumulator architecture like the Mary. AC is the one has AC accumulator register, right? Or you can use a general purpose register architecture, which is in assembly, Microsoft Assembly and MIPS, they have general purpose register. If you are taking assembly class, you already know that. In choosing one, I mean, all of them is the same, right? It's going to give you the same thing, but it depends on architecture. In choosing one over the other, there's a trade-off, right? Simplicity and the cost of the hardware, right? And also the speed and ease of use. So in stack architecture, instruction and operand are implicitly taken from the stack. We'll see example. Let's see. Yeah, I think this is your stack. So stack architecture requires us to think about arithmetic expression a little differently, right? So we used to have the infix. This is called infix. Z equals to x plus y, right? But stack, we actually want to look at postfix, like z equals to xy plus, right? So, right. So like this. So advantage of postfix notation is that you don't need parentheses, right? So this is we already customized to this infix, right? Times parentheses first and times another parentheses first, get two products and add to get the sum. But if it's infix, if it's postfix, you don't do that. There's no parentheses. You have to push x and y into the bucket like stack. So let me see if I can draw, which is probably on the board is maybe easier, but let's try. I have a bucket, so I push x in the bucket, right? Okay, and now I push y, right? And then I run into what? Operation name plus. When I see operation, I have to pop. Okay, I have to pop. Whenever you see operation, you pop them, right? And then, yeah, you pop both of them, and then you sum. Now you get the sum. When you get the sum, SU and sum, then you push the sum back into the bucket. Now in the bucket no longer have x, no longer have y because we pop them, right? So now we push that back into the bucket, right? And then you start to do another operation, which is what? Now it's xy. But if we talk about xy multiply, we find the product, right? And then you start to push wu in the bucket, right? In this case, correct? So let's say this is the product, right? Instead, right? So so I have the product in here. We call P, right? We're gonna call this P instead now. Because we pop X and Y out, we get the P, we push the P in. Now we have P with what? In the question say WUX, right? Then you start to push W and U and X, right? Into the bucket, right? And then you have multiply again, right? That X means multiply. So now you have W and you have U, and you happen to find the operand again, operator. Then you multiply the pop W and U out, pop those two out, and find the product, right? And then you get that product, so you don't have no more W and U. You push the new product in, right? P2. And then you start to read more, you get operand, right? You get 2 plus again, you pop 2 more, which is P1 and P2 out. Now the bucket is empty, and then you have to find the sum of P1 plus P2. Then you get the sum. That's how you get the answer, and you push the sum back into the bucket. So this is stack for architecture. Make sense? Okay. So that's just example with the numbers. Right, that's the stack. You push 2 and 3, you see the operator, then you pop 2 and 3, find the sum, you get 5, push that back. And now we start to do 6 and 3, push them 6 and 3 in, and pop them because we see the operand. 6 divided by 3, we get 2, we push 2 in, right? And then we see another operator, which is 3, subtract and push the result. We get 3. Which is the same architecture that we can do, right? If we want to do stack operand, right? Let's see how to evaluate an infix expression using different instruction format. With a 3 address. So this is with a 3 address. This is like MIPS, right? So x times y plus w times u. So you're going to multiply x and y. We have the the opcode as mul. and store the value into R1. See that? Like maybe multiply W and U and store the value into R2. And then you add R1 to R2 and store the result into Z. That's easier, right? And now let's look at, this is the 2 address. This is what 3 address, right? Instruction set architecture, I say. This is 2 address instruction set architecture that's using in Intel and Motorola. That one using in mainframes, right? So this, okay, if you have just 2 instructions, then you probably have to have more lines of code. Like Mary, to do this is going to be even more than this, right? That's because that's one, right? One address, right? So this one, you have to load X to R1, and then you say multiply Y, right? Multiply Y to R1 because you load, right, to R1. And then you load W to R2 and multiply U to R2, right? And then you add R1 to R2, then you get a result in R1. That's why you move R1 to Z. So in this type of architecture, we always have the result in the left. Okay. And this is like a Mary one. To do this, you have to load X into AC. You rely on AC accumulator, right? And then multiply Y to AC, store AC to temp, right? And then load W to AC, multiply U to AC, and store, and then add to temp, right? Add temp to AC, right? And then move store Z. All right, so that's Mary. And this is the same thing, but using stack architecture, right? Stack architecture is going to be push X, push Y, multiply, push W, push U, multiply, and add and pop Z. They'll give you the same result, but different architecture. Yeah, the first one is the 3 register. It looks simpler because you have, but you have to make more spaces. So that's a trade-off, right? I mean, if you are in the limited spaces, like in the space,
Yeah.
where you don't have enough resources, right?
You're using a
200 terabyte drives.
Yeah. I mean, if you're an assembly, you're already pretty efficient. You can make
memory, not
things.
stored.
Yeah.
Yeah.
Oh, yeah.
Yeah.
That's the first one is actually more
I mean,
reliant on the
in the
CPU.
past, the memory is so expensive, right?
Yes.
That's why this type of thing is very useful, right? Because we talk about we don't have IC. Remember, we look at generation 0, and then this is they're gonna look at it. Wow, this is awesome. But now we look at it, no, because we have too much memory now, right? I mean, this memory is now cheap and small. That's why, right? But if you don't have the memory, then you're going to appreciate that.
Like 4 years ago.
All right, so instruction format. Let's look at this. So we have seen how instruction length is affected by the number of operands, right? If any instruction set, not all instructions require the same number of operands, right? In any instruction, that's right. In any instruction set, this key is very important. In any instruction set, you actually not require the same number of operands. You agree? Okay. Right, like, right, store you don't need, right? So let's say like halt, right? Halt you don't really need, right, operand. So you're wasting the spaces right there, right? When fixed length instructions are used, right? One way to recover some of this space is to use expanding opcodes. So meaning that we can have more opcode now based on the limit that we have by taking advantage of the waste spaces right there. So a system has 16 registers and 4K of memory. We need 4 bits to access one of the registers. Right, 2 to 4 is 16, right? We also need 12 bits for memory address. This is exactly like Mary, right? If the system is to have 16-bit instructions, we have 2 choices for our instructions. So this happened to be 16-bit instruction, right? So how many address here? 12 and 4 opcode, right? So this is Mary, right? Another option is 4 opcode and 4-bit address 1, 4-bit address 2, and 4-bit address 3. So if we allow the length of the opcode to vary, we could create a very rich instruction set. Right, in Mary we have the fixed rank, right? So now we said we can have R1, R2, R3, right? Registers, right? So when you look at opcode, it's going to run from 000 to 1110, right? When it's come to 3 registers, right? So we're going to have how many? From 000 to 1111, or about 15, right? Is it? 000 to, right? Right, 16 minus 1, right? So we have 15 right there, right? And then we also require to have 1111 to make it to separate the sections, right? Otherwise we don't know, right? When it start to 111, we talk about 2 registers, right? R1, R2. Make sense? And we use that as call as escape to separate them, right? Then R1 to R2, we actually can have up to 1101. Because we have to preserve 1110 for escape again. Because we have to escape for 1 register. Right? So that means this one is going to be 14, right? 14 instruction with 2 addresses, right? Right, we preserve that for escape, right? Then when we escape that, then we know that whenever it start with 10, we know this is 1 register, right? Make sense? And then that's gonna run up to where 11110, right? And this is gonna give you, because since this is start with 0, then this is gonna be 5 bits, so it's 31, right? Right? It's minus 1, right? With that escape 1111. When we get to that, so this is going to be 0 address code, but we can have up to 16 instruction right there. So we can have many instructions if you add them all up. Oh, to separate the sections, right? When you start with 1111, those are 2 address codes, right?
So the first one is 3 memory addresses or 3 registers loaded. second one is
two registers. And this escape, like when the 4, 5, 7 first bit are ones, those are for one register address code, right? And this is when 11, right, bits are one. Those are one register code, right? Make sense? And this is escape for when 12 bits are one. So those are the, you can use this for halt when you don't need, right? You don't waste spaces anymore. So this is what I'm looking for the final project. That's what you try to get together. Design expanding your memory with vary instruction codes. Then you can add more opcodes to your memory. Right? When you do halt, you actually can use this zero address codes because you're wasting that 12 bits. Now Mary can do more than, right, 2 to 4. That's why I said, okay, let me drop that final project. It looks like I have it for a couple years and not many people can accomplish that. We did that assignment. He keep asking for final extra credit. That's what you've been asking for too. That's the final project. Now you know that what I'm looking for, right?
But someone did complete it, right? Fully completed all the work. Staring at me, so that means like it was a 80%.
I got about 20% something like that. There's the framework. Kind of looks up.
Actually, someone make a compiler, but not the, yeah. Someone make compiler and also, yeah, the create his own editors and compiler to run on his machine.
From Sourceful.
No. Maybe who knows, right? But I think he did it because he can explain, which is fine. If you understand everything you explain to me clearly, you test, I delete some lab code, you can fix it. So as long as you understand what you're doing.
Without giving a work side.
Because we don't want to reinvent the wheel, right? We create the libraries all the time. It's object oriented. Right?
Isn't work moving towards like what was that, symbol oriented? I thought it was.
Alright, so given 8-bit instruction, is it possible to allow the following to be encoded? 3 instruction with 2 3-bit operands. So we said 8-bit, right? 1. Faster.
Flip a coin, isn't this one gonna work?
Let's see here.
Okay.
1, 2, 3, 4, 5, 6, 7, 8. So we can look at.
You're about to huff the pen.
3 instruction, okay. 3 instruction, this could be what? 00, 01, 10. What's that 3, right? With 2 3-bits operands.
Yeah.
Right.
So that's what, 8 bits?
1, 2, right? Alright. And if we want to do it vary, right? 4-bit operand with 2 instruction. 4-bit operand with.
Yeah, no, doesn't work. You run out of bits. 3 more bits?
So let's talk about 4 bits, right? with how many instructions?
2 instructions, 1 4-bit operand.
So we need the escape, right? So this and escape could be 1 1, right? That could be your escape, right?
Yeah.
Escape. And then we can go to 1 1 0 0, right? 1 1 0 1, right? So that 2 instructions to work with 2 bit, right? I mean with one 4 bit, right? Yeah, right. 1 4 bit output, right? So how about 4 instruction with 1 3 bit operand? 1 3 bit operand. So we're looking at this guy. We have all more colors. So this will be your R4. Yeah. And then we need an escape, right? 1 1 1. That could be an escape all ones, right?
Yeah.
2 1 is 1 escape, right? All 1 is another escape. So 1 1 1. Can you see it?
Not really.
It can stand. Is it better now?
Yeah.
So 1 3 bit operand 4 instruction. It should look like check there. Right? O, that's 1 instruction, right? Right? And then O 1, right? 1 1 1 1 O and 1 1 1 1 1. That works, right? We have 4 instructions. We get 4 from here, right? We get 2 and then we get 3, right? So that's good. Any questions? So with 8 bits we can have up to 9 instructions.
So default, we have 2 instructions, right? And if
What do you mean by default?
okay, the first
2 registers.
2 registers. So if we hit an escape,
Then
it's
whenever
1
we
1
see 1 1, we know we hit into 1
register.
register with 4 bits.
We can
And then we can have up to 2 more instructions.
and if we have 1 1 1, we have 1 register with 3 bits.
Right.
Okay.
And then we can do mix and match, right?
Yeah.
This could be the 1 register architecture. This could be 2 register architecture. Right, then we can expand our instructions. I don't know why human who thought like this, what they do with their time. I will never think of this by myself.
Oh, this is very true.
Right? We are very busy. We never have time to sit and really think about this. Maybe
We locked them in solitary confinement for a while.
I was going with savant, but solitary confinement. Okay.
Showers. Lots of long showers.
Oh,
You
prison
thought it
and
was different
showers
hours.
Right? Can you imagine that you will really get to that if you're not reading or see it?
In like 80 years, maybe? Fiddling around with it, saying, hey, maybe there's a better way. After 80 years, maybe I might get that. But
I don't.
I'd rather read it in a book.
Well, I mean, like, maybe some person had a problem with the number of instructions you get.
Yeah.
With a very limited, and so, like, they figured it out through, like, pasting a bunch of, like, zombie code.
He's a better man than I. I'd probably give up after an hour, go get a beer, and
Chill.
yeah. We consider that as
So this is the same explanation, right? Okay. So instruction fall into several broad categories, right? Data movement, arithmetics, Boolean, bit manipulation, I/O, control transfer, special purpose. Can you think of some example of each of these? Right, those are those are instruction, right? Add, subtract, Boolean, what's that? Skip, con.
Compare two things.
Bit is shift left, shift right. SSL, SSR, input output, that's the move to register. Control transfer.
That's jumping.
Yeah, jump, yeah. And special purpose. Addressing modes specify where an operand is located. They can specify its constant, a register, or a memory location. Just like the one that MIPS show you can move into and form, right? From memory to register, to register, from register to memory. No, it always has to go to register first. There's no way you cannot just say 5 when 5 is not in your brain. Right? You cannot say the word from the book when you not put in your memory and breathe it out. Just like that, right? Or you Oh, another word. Okay, I have 2 notebooks. I want you to copy the contents from notebook 1 to notebook 2. Can it actually go right there, right away, without storing through your brain and then, right? So that means you cannot move from node A to node B. You have to move from node A to brain and from brain to node B. You have to have 2 steps. You can do directly from brain to node A, brain to node B, but you cannot do node A to node B directly, right? That makes sense? Yeah, there's no way to move from memory to memory. That is assembly, right? That you learn. You cannot add memory 1 to add memory 2. You have to move memory 1 to register, move memory 2 to register, and then you add register. I mean, you don't have to move memory 2 to register. Save memory 1 to register, then you can add memory 2 to register 1. Then you save one line of code. Okay? Once it's in register, right? All right, they can, now the actual location of an operand is its effective address, right? Certain addressing modes allow us to determine the address of an operand dynamically. Okay. So now they talk about immediate addressing, and is where the data is part of the instruction. So like if I want to add 5 is the data, right, to the accumulator register, right? So that's immediate addressing. Direct addressing is where the address of the data is given in the instruction, right? I can say add 101, go to address 101, right? Add I, something like that, right? Indirect addressing here, give the address of the data in the instruction. That means I go to 100, but 100 store another address 101. It's how to jump there again, right? Register addressing is where data is located in a register. The data.
32 bits and it has a 16-bit part and an 8-bit part.
And this is just indirect addressing for register, where we just store the address of the data. And we have indexed addressing, uses a register as an offset. It's going to have an example here, okay? Like you pretty much just, that is an offset to another address. You add 10 more to jump to that address. Base addressing is similar, expect that a base register is used instead of an index register. The difference between these two is that an index register holds an offset relative to the address given in instruction. A base register holds a base address where the address field represents a displacement for this bit. So let's look at, this is an example, okay? It's going to show you, this is going to be in your test, and Colin just walk out. Okay. So the instructions show what value is loaded into the accumulator for each addressing mode, right? Load 800. Immediate, right? Yeah, 800 is just like the value, the data. But direct is going to be 800, then 900, right? But indirect is going to go to address 900 as address, then put 1000, right? Index is going to be, is the offset, right? It's going to be 800, right? So you get 7, you jump to 1600, right? Which is you get 700 as a value, right? See that? Because you add offset to your base, right? 1600. But you get a value, right? Of that address.
Isn't index adding the value at 800 to memory location 800? So shouldn't it be 1700?
1 second.
Index, it uses the value stored at 800.
So it's,
as an
okay, index addressing use a register as an offset, which is 800, right? Which is added to the address in the operand. So
Shouldn't it be 800 plus 900?
to the address in the operand, right? Added to the address in the operand.
Yeah.
So which one is it? Which one is an offset? Uses a register as an offset. So register as an offset is this guy. This guy is the register as an offset, right? Which is 800. Which is added to the address in the operand.
So it would have to be whatever's already in the
And this is the address 800. So 800 add to 800 becomes 1600. We're not adding to the value, we add to the address. Because it's like the array, right? Index.
Yeah.
So you get 1600. So that's why the value is 700. So for a test, review this section. Okay. All right, so instruction pipelining. I mentioned that last time when we look at the timing diagram, right? So in the CPU, we have what? Fetch, decode, execute, right? Fetch the instruction, decode the operand, execute after you map, right? You translate and mapping to that pass 1 and pass 2, right? Table. Then you get RTL, right? And execute. So this similar step can often be executed in parallel to increase throughput. There you go. I told you. You can do it at the same time. That means you can do execute it in parallel. Such parallel execution is called instruction pipelining. Okay. we call ILP, which is instruction level parallelism. So let's look at, suppose we have, so first we understand that the fetch decode cube can broken down into 6 steps. Fetch instruction, decode opcode, calculate effective address of operands, and then fetch the operands and execute the instruction and store result. So now we're gonna break that, right? So these are cycles, right? And these are the S1 to S6 that we said, right? So S1 fetches, S2 decode, S3 determine the address of the operands, right? S4 fetches the operand, S5 execute instruction, S6 store, right? So we have that S1 to S6. Like this is the CPU cycle when clock trick, right? For every clock cycle, one small step is carried out and the stages are overlapped. This is pipelining. Instead of wait for the whole thing done, get S1 to S6 the next set, right? Instead of doing that, you could just do parallel. While you're fetching instruction 1, you can fetch instruction 2. While you fetch instruction 2, you can decode up, right? Instruction 1, right? And while you do calculating for address that, you can actually decode instruction 2. Then instead of taking 12 cycles to complete this, it's short to 7 cycles. Make sense? I think we time, right? Our time has called that we need to go home and have some good food before study. All right, so it's good point to stop. This is just going to come back with a calculation next class, and then we pretty much done. And then we can, yeah, we should not take long for this class. We can go to chapter 6 and talk about assignment.
The assignments only really located in chapter 6. So for example,
And I would encourage you to read chapter 6 and assignment before you come, because it's kind of a little bit confusing.
So that's all.
The assignment
that's
6.
what I was about to ask. Yes, this presentation is entirely. No, I would decide one to make it. You remember the codes we got?